Hi ladies and gentlemen, this is Miss Skokin. We are going to be talking in more detail about reflections, which is one of the isometries or rigid transformations that we learned about in the previous section. Our objective is identify and draw reflections. Our vocabulary is isometry, and I just talked about that. It is a transformation that does not change the shape or size of an object or an image. All right, let's take a look at the warm-up questions. Using one of the vertices of triangle 1, that means one of the points on the triangle, use arrow notation to write the mapping rules for transforming to the other 3 triangles. So you may remember from the previous section that we learned all about mapping rules, and they are the statements that start with an X and Y and indicate what change has taken place to each one of the points. So knowing what a mapping rule is supposed to look like, starting with point XY and mapping to some indication of what's going to happen to the original X and what's going to happen to the original Y for us to go from one triangle to the other or one point to another. In this case, we're going from point 1 to point 2, or I'm sorry, triangle 1 to triangle 2. So let's pick a point to use. And I'm going to choose that lower right-hand corner, which is located at 3, 1. And if I want to go from that triangle number 1 to triangle number 2, what would be the corresponding point, and what is the mapping that would take place to go from triangle 1 to triangle 2? Now you may realize already that it's a reflection to go from 1 to 2, and the corresponding point to the one that I just selected is this point right here. And this one is located at 3, -1. So what happened to the coordinates? Our XY coordinates went to the same X coordinate, but the opposite Y coordinate. Now, I've done example 1 for you. What I'd like for you to do is continue, pause the video, do questions 2, 3, and 4 of the warm-up, and then turn the video back on when you're ready to check your answers. But you're going to use that same type of thinking to figure out how to map one triangle to the next. All right, see you back in a minute. So you can see 2 of our transformations were reflections over the x-axis, and 2 of them were reflections over the y-axis. If you have questions about this, please ask in class, and let's move on to an explanation of isometry. We talked about this just a minute ago, but an isometry is a transformation that does not change the shape or size of a figure. We have different kinds of isometries. Reflections, translations, and rotations are all isometries. We also have other names. They can also be called congruence transformations because when we do those types of transformations, the image is the same size and shape as the pre-image. Also called rigid motions, also called rigid transformations. So just a few different names of basically the same thing. Now, there are some vocabulary that you learned, some vocabulary terms that you learned in middle school, specifically, for example, a reflection you called a flip. We're not going to call it a flip anymore. We are going to call it a reflection. And the others that you learned were a translation you called a slide, and a rotation you might have called a turn. So we're going to use the proper geometry language for those now, not the middle school versions. So a reflection is a transformation that moves the figure from the pre-image to the image by flipping it across a line. So we typically have this line of reflection, and what that means is it's got to be as if you could put a mirror in between the 2 figures and it looks exactly the same on the 2 sides. Or it looks, I shouldn't say exactly the same, it looks like a mirror image on the 2 sides. So we look at example 1, we're trying to identify whether or not these are reflections, and we see that first image, the red and the blue, and imagine that I put a mirror up between the 2. Is one a mirror image of the other? And in this case, the answer, of course, is no. One is not a mirror image of the other. And the reason is because we can think of the little post towards the bottom. On the blue pre-image is on the right hand side, and on the red image is also on the right hand side. So they're not actually mirror images of each other. This actually looks like a translation, or it's a slide from one location to another. So this one is a definite no. So the image does not appear to be flipped, so we do not think that this is a reflection. When we look at the number 2 example, we draw that line of reflection, and in this case it does look like an exact mirror image, one side and the other side. So this time, yes, the image does appear to be flipped across a line, so we know that that means it is a reflection. So before we go any further, I just want to remind you what the words preimage and image mean. The pre-image is before the transformation has taken place. And the image is what we call the picture after the transformation has taken place. The formal definition of a reflection is a transformation across a line. The line is called the line of reflection, so that the line of reflection is the perpendicular bisector of each segment joining each point and its image. That sounds very complicated, but really all it's saying is that when we have a point, such as point A, this is the pre-image, if you can imagine the shortest distance between point A and the line of reflection is the length of that segment, then all we're going to do is draw another segment the exact same length in the opposite direction over the line or across the line of reflection, and we're going to call that one A prime. And the line of reflection ends up being the line that splits segment A prime exactly in half. So when we look at example 2, we're trying to not identify tangents of circles. That was definitely a typo. It should read drawing reflections, so please correct that in your notes. Anyhow, we're going to take a look at these 2 pre-images and draw the reflection of the pre-image across the line. So as we said, what we're going to do is we're going to start out with the perpendicular and drawing the opposite to the perpendicular distance to create a point. It's going to have the same length so that we end up having a bisector of that segment. And so we're going to draw 3 of them because of course there are 3 points on this triangle, and then we're going to be able to draw the image of the triangle. So let's draw some segments between these points that we created, and then we will have the image. And you can see that those 2 figures look exactly alike. They're equally distant from the line of reflection. They have the same size and shape. They're just mirror images of each other. So what I'd like for you to do now is pause the video. Using that same thinking, using that same method, I want you to draw the reflection of the quadrilateral across the line. Turn the video back on when you're ready to check your picture against my picture. See you back in a minute. I drew this one with thinner highlighter lines, and it's funny, it kind of looks like a funny 3D effect. But anyhow, we do see that it's the pre-image and the image are exactly the same size and shape. But obviously their positioning has changed and their orientation has changed. So they're kind of facing in a different direction. And that is how we draw reflections. Remember that each one of those has to be a perpendicular to the line of reflection. So each one of those is a perpendicular segment or perpendicular distance. All right, that does it for example 2. Let's take a look at example 3 now. Example number 3 says we have 2 buildings. One is located at point A, one is located at point B, and they are to be connected to the same point somewhere on this water line. And we want to use the least amount of pipe possible. So we want to minimize the distance from that point on the water line to point A and from that same point on the water line to point B. The method for doing that is to first reflect the shortest distance away, which in this case is from point A to the water line. So if we can imagine that all we want to do is create a point A prime, which is the reflected point, and we can see that this is the reflection of point A. And then we want to connect point A to point B, draw a segment between them. And that location we're going to call point X. We could really call it anything, but it's convenient to call it point X. So what this is doing is this is saying that the distance from A to X and then from X to B is the shortest possible distance, or the least amount of pipe that we would be able to use to connect those 2 points to the water line. We have another example that you're going to try independently. You're going to pause the video and then try it out using that same methodology, and then turn the video back on when you're ready to check your answer. So see you back in a minute. So we started out by reflecting the shortest distance, which happens to be from B, point B or campsite B, to the river. And then we drew the segment from point A to point B prime, the reflection or the image of the preimage of point B. And then that intersection with the river and segment AB prime is where we're going to locate the connecting point of the two trails at the river line. Now let's take a look at some reflections in the coordinate plane on the next page. So remember, a coordinate plane we sometimes call an XY axis or a coordinate grid. What we're going to be looking at is 3 different types of reflections this year. There are others. You can reflect across other lines, but this year we're only going to be taking a look at reflections across the x-axis, reflections across the y-axis, and reflections across the line y equals x, which is the diagonal line that goes through the origin and has a slope of 1. When we reflect a point, and remember, anytime we're going to reflect an image, we have to reflect point by point by point. So when we reflect a point across the x-axis, notice what happens. The x-coordinate stays exactly the same, but the y-coordinate goes opposite from what it was. So when we reflect across the x-axis, the y-coordinate turns opposite. When we reflect across the y-axis, and here's the mapping statement, just so that we take a look at what the entire mapping statement looks like. When we reflect across the x-axis, x stays the same, y goes opposite from what it started out. When we reflect across the y-axis, the y-coordinate stays the same, and what changes is the x. The x-coordinate is opposite from what it started out. So the mapping statement is x comma y, then our mapping arrow, the opposite x, and the original y. Interestingly, when we reflect across the line y equals x, what we see happening is the x becomes the y coordinate, and what started out as the y coordinate turns into the x coordinate. So it's the exact reversal of the x coordinate and the y coordinate. It seems a little counterintuitive, and I recognize that, but this is how it works. And if you were to try to figure it out yourself, first by drawing the reflection from point P to point P prime, you would end up coming up with that same reversal of coordinates. So let's take a look at example 4 and practice this new information on an actual coordinate plane with some points. Example 4 says we're going to be drawing reflections in the coordinate plane, and we specifically will be reflecting the figure with the given vertices across the given line. For part A, we have 3 points, x, y, and z, that we are going to graph before we do anything else, and then draw the segments between points x, y, and z to create a figure, which when it has 3 points, we know it's going to be a triangle because it'll have 3 sides, unless, of course, all 3 of the points would be collinear. So anyhow, let's pause the video and draw the triangle first. Remember to label your points with their point name. Here's our triangle XYZ, and you can see I've colored it in with a highlighter only because it's going to make it a little bit easier for us to see the reflection. Now notice that the instruction that we're given is we're reflecting over the x-axis, and we learned just a minute ago that we have a mapping rule for that, and the mapping rule says that point x comma y, when we reflect over the x-axis, x comma y maps to x comma negative y. So the x coordinate stays the same, the y coordinate changes to the opposite. So what we're going to do is write down our new points. That mapping rule is guiding us to be able to write down the reflected points coordinates. So x stays the same, y goes opposite. And x stays the same, y goes opposite, x stays the same, y goes opposite. So now what we've got is the 3, whoops, this is y prime and z prime, sorry about that. So now what we've got is the 3 coordinate pairs for the 3 transformed points to be able to draw our reflected triangle. So let's go ahead and plot those points. X prime is going to be located at 2 comma 1, so that's x prime. Y prime is at negative 4 comma 3, that's y prime. Remember, always label your points. And z prime is located at 3 comma negative 2, z prime. And now we're going to draw the segments between these points, connect those points together so that we can actually see the triangle that we have reflected across the x-axis. I'm also going to label the red one is our image, and the blue one, the one that we started out with, was our pre-image. So we identified the original figure and graphed it. We figured out the mapping rule based on the instructions that we were given to reflect over the x-axis. We found the coordinates, the transformed coordinates of the image, and then we plotted those points and connected them to create the fully reflected image of the pre-image triangle XYZ. What I'd like for you to do, of course, is for question B, pause the video and do exactly those same steps. First, draw the pre-image, labeling each of the points. Then you're going to figure out the mapping rule. Then you're going to figure out your new points, and then you're going to plot those new points for the image. The only thing I'm going to get you started with is we are going to plot that line y equals x, and I just want you to be able to see what you're reflecting over, and it'll make it a little bit easier to see the reflection once you do plot those extra, or the pre-image and the image. So I'm just going to draw a dotted line right here where we have the line y equals x, and I'm going to label it y equals x right there. Okay, pause the video now and turn the video back on when you're ready to check your graph against mine. See you back in a minute. Okay, so we started out by graphing triangle RST, which is our pre-image. Then we figured out our mapping rule, which is x comma y goes to y comma x when we reflect over the line y equals x, which is the black dashed line that you see. And that allowed us to figure out the coordinates r prime, s prime, and t prime for our reflected points. And then We drew the segments connecting those points so that we would be able to draw the reflected image of triangle R prime, S prime, T prime. Time to work on practice problems for reflections. And remember, if you have any questions, I hope you wrote them down in your notes so that we can discuss them in class.